Mid-June 2026, as the southwest monsoon transitioned across West Bengal, the atmosphere over the region became extraordinarily volatile. These reports detailed a high-frequency, violent vibration synchronized with the lightning strikes, a mechanical shudder far removed from the slow, rhythmic swaying common during monsoonal winds. This map tracks the rapid, jagged advancement of the southwest monsoon over the sub-Himalayan region. The boundary lines push aggressively northward, but this fast-moving air collided directly with an unusually severe, localized heat wave parked over the Gangetic Delta. Look at the color contrast on this cumulative rainfall map from early June. The deep red areas right at the monsoon boundary indicate a severe 23% rainfall deficit. The soil was baking, pushing surface temperatures in Assam to 39.4 degrees Celsius. The shaking bed is the terminus of a multidisciplinary energy cascade, a chain reaction connecting meteorology, acoustics, structural dynamics, and human neurobiology. The extended pre-monsoon dry spell severely depleted soil moisture across the delta. Without water evaporating to cool the surface, the Earth absorbed an immense amount of solar radiation. This triggered a massive sensible heat flux. The dry, baking ground transferred its thermal energy directly into the adjacent air, establishing an exceptionally warm and deep planetary boundary layer over the state. When the relatively cool, heavy air mass of the southwest monsoon arrived, it acted like a wedge. It plowed into that superheated boundary layer, forcing the hot air violently upward in a rapid thermodynamic uplift. Concurrently, the global climate was transitioning toward an active El Niño phase. This generated extreme vertical wind shear right at the collision point, with upper-level winds tearing horizontally across the rising thermal column. The combination of extreme heat flux and aggressive wind shear forced the chaotic air masses to organize. They rapidly formed deep mesoscale convective systems, towering cumulonimbus cells capable of producing severe thundersqualls. These storm cells act as highly pressurized atmospheric engines. They store the immense potential energy required to trigger downstream mechanical damage. Inside the upper reaches of these storm cells, strong updrafts force a continuous collision between small hail particles and lighter ice crystals. This constant friction strips electrons, creating a massive electrical charge separation. When the insulating capacity of the air breaks down, the stored electrical energy discharges. A cloud-to-ground lightning strike surges downward, instantly superheating a narrow atmospheric channel to 30,000 degrees Kelvin, 5 times hotter than the surface of the sun. The air molecules trapped inside that lightning channel have no time to expand gradually. They explode outward at supersonic speeds. This diagram illustrates the resulting acoustic shock. It is an N wave. The supersonic expansion creates a sharp, discontinuous rise in pressure, followed by a linear drop below the atmospheric baseline into negative pressure, forming an N shape. This shock wave carries immense mechanical energy, functioning as a physical force rather than simple sound, identical to the signature of a supersonic aircraft's sonic boom. Normally, much of this low-frequency sound energy dissipates into the upper atmosphere. But in the wake of these monsoonal storms, a temperature inversion, a layer of warm air trapping cooler air below, bends the upward-traveling sound waves back toward the ground. This acoustic ducting traps the pressure wave. It transforms thunder from an ambient rumble into a highly concentrated, surface-level mechanical battering ram. When this trapped N wave finally impacts a residential area, the energy transfers through 2 distinct pathways. Airborne acoustic waves exert physical force against the exterior walls, while a ground-borne wave couples directly into the foundation. As the atmospheric shock wave slams into the Earth's surface, it generates implosive microseismic events. The energy penetrates deep into the soil, propagating outward as seismic Rayleigh waves. The efficiency of this energy transfer depends on a precise alignment of frequencies. This spectrum chart shows the acoustic overpressure input from the thunder, concentrated heavily in a low-frequency band between 10 and 30 Hz. Now, look at the geological profile of the Gangetic Delta. The wet clay and sand substrates possess a natural shear wave resonant frequency right around 15 Hz, dropping perfectly inside that acoustic input band. and the typical concrete-framed residential structures built over this soil exhibit fundamental bending modes right at the 20 Hz mark. The environmental and structural resonances completely overlap. The building's floor absorbs these waves instead of reflecting them. This alignment causes the concrete to act like a complex vibrating plate. During these squalls, the structure is not swaying from the surface wind. Its entire foundation and flooring system are actively resonating with the thunder's deep seismic frequency. Up in the bedroom, the structural resonance of the concrete floor is technically a micro-vibration. To a person standing upright, it would barely register, but the bedroom furniture introduces a secondary spring mass system. A traditional steel coil spring mattress possesses incredibly low structural damping. Those steel springs act as elastic oscillators. They capture the transient microwaves traveling through the floor and physically multiply their amplitude. Lying flat provides highly efficient mechanical coupling. The supine position presses the entire surface area of the body into the mattress, simultaneously activating a massive network of somatosensory mechanoreceptors from head to toe. The final variable is neurological. These events occur late at night, catching the subject asleep or suspended in the highly vulnerable hypnagogic and hypnopompic transition states between waking and sleep. The sudden, blinding flash of lightning and the immediate violent crack of near-field thunder completely shatters the brain's sensory gating mechanism. The amygdala, the brain's threat detection center, triggers an instant adrenaline surge, but because the motor cortex remains partially paralyzed by the natural mechanisms of REM sleep, the body cannot react. This split screen illustrates the resulting sensory-motor mismatch. On the left is the physical reality, a bed frame exhibiting faint, low-amplitude microvibrations. On the right is the neurological perception. The sensory cortex synthetically over-amplifies those real physical inputs to match the brain's elevated threat level. The violently shaking bed is a real physical event that has been neurologically hijacked, a minor environmental microvibration exponentially magnified by a gating failure in the human brain. The phenomenon requires a precise chain of causality, a thermodynamic monsoon collision generating a ducted supersonic N-wave, coupling with wet clay structural resonance, and culminating in neurosensory sleep amplification. Because we cannot control the meteorological conditions or the human sleep cycle, preventing this sensory disturbance requires breaking the chain strictly at the mechanical level. At the macro-engineering level, this means stiffening residential concrete floor spans. Adding mass and support pushes their fundamental bending frequencies safely above the environmental 10 to 30 Hz coupling zone. A more localized intervention involves completely decoupling the bed frame from the resonating concrete slab. Installing high-density rubber vibration dampening pads under the load-bearing legs stops the shear waves from entering the frame entirely. Finally, we have the material intervention, replacing undamped steel springs with highly absorptive viscoelastic materials, such as dense memory foam or latex. These viscoelastic materials possess high internal damping. They absorb the upward mechanical energy and safely dissipate the structural shear waves as trace amounts of heat before the vibration can transfer into the human body. We must treat extreme meteorological events as complex mechanical inputs coupled to our built and biological environments to engineer residential infrastructure that protects both the physical structure and the human nervous system.